The Institute for Quantum Computing is an institute at the University of Waterloo, whose aim is to develop the science of quantum information, and that includes quantum computing, quantum communication, quantum metrology or quantum sensors, and some materials that are essential to build devices that use quantum mechanics. So it's an institute whose first goal is to do the research, the basic research related to quantum information. The second one, to train a generation of students and scientists and engineers who think quantum. We all kind of grow up and we are learning Newton's mechanics or classical mechanics, even if most people don't call it that way. That's the way we understand how to control our car by using our bicycle or whatever, flying in an airplane. But really the world at its very fundamental part behaves differently. Like atoms and molecules and electrons and protons have a different set of rules. And then we want to use these rules to manipulate information. I'm happy you say why harness these instead of why do they behave that way, because we just don't know why they behave that way. The world is built in some way, and maybe there's a fundamental reason that one day we will discover that it cannot be otherwise. It had to be this way. But right now, we just kind of explore the world and try to understand how it works. One of these properties of quantum mechanics is called the superposition principle. In the physics of Newton, or what I call classical physics, we think of objects made of particles, and particles are little things that are at a given position in time and at a given velocity. This works very well to describe most of the world that we interact with in day-to-day, except people like me and my students and my colleagues who suddenly go in labs and isolate these particles very well and try to see how they work. And what we find is there's something called a superposition principle. These fundamental particles of nature can be at more than one place at a given time. So a single system can be here and there at the same time. We are trying to use this property, the superposition principle, and use it to compute. And so we kind of discovered that if we use these properties, we can build computers. And so we found that by using the rules of quantum mechanics, the theory that described this kind of very small part of the world, if we use the rules of quantum mechanics to compute, we can solve problems which seems to be intractable with classical computers. And suddenly it tells us that if we can do that, there's a wild world of information that will open to us that we haven't, which is totally surprising because it is mind-boggling what we've seen in the last 50 years with the computing or information. This turned into computers in the 1970s and 80s and the cellular phone that we have today. You and me have grown up where we had neighbors and our friends were neighbors. Our kids grow up where their friends can be in France or in Japan or in South America. Instead of having a little local village, we have the Earth is a global village, all putting this together. That changed the way that people think, the way we behave, and what we think about the future. So this incredible change of how we conceive the world because of this information revolution. And suddenly quantum mechanics comes in and tells us things can be very, very different. We can navigate even so much more information that these classical computers cannot do. We don't have a full-fledged quantum computer today, and until we have one, you should have a little skepticism, although I really believe we will have one, but this is a belief and not a scientific data, and quite a distinction between the two. In the 2000s, a lot of the work of the director of the Institute was to convince people that this was really an important field. And we seem to have done a very good job because people now there's investment from government, industry, many universities across Canada and around the world have a group of quantum information. Now this is different. Now a lot of the work is really to develop these ideas to, in part, better understand where the power of quantum computing comes in, find new class of algorithms that kind of quantum computing could help and kind of make more efficient, and then turn into how do we rebuild these devices and building them. So maybe 20 years ago, we were really asking, how can we really build these things? Now we have a bunch of blueprints and people are in lab trying to show them, and industry. Building quantum computers has become complex enough that it is hard to make this in a university, in part because it takes a long time to go from the first steps to the device that we have today. Generation of grad students are 3, 4, 5 years, and that's a little too short. We can make proof of principle of certain mechanism or certain things, but it is really the IBM, Googles, and Xanadu, and those that are really kind of putting all the engineering together and kind of developing these ideas to get devices. Not the one that we finally want, but enough to give us confidence that we are on the right track. A lot also of understanding where the problems and the challenges are and get over them and kind of moving forward. My first piece of work on quantum computing was to try to prove that they would never work. Probably 10 years after, I started to work on quantum computing. I went to a conference in Santa Fe. My mentor at Los Alamos National Lab, Wojciech Zurek, told me there was this conference on the physics of information. And I initially said, I don't want to go there because I don't know anything about the physics of information. And Wojciech told me, there's really neat people going there. Like, what is it? It'll take 2 days. And it was kind of 45 minutes away from Los Alamos. He says, just go. And so I said, okay, I'll go. And it turns out that was the first time I heard about this algorithm called the Shor's algorithm, which is crucial for quantum computing. It's related to factoring numbers, which are product of primes, using a quantum computer, which turns out to be an algorithm on which cryptography, in fact, most of today's world cryptography is based on the difficulty of factoring numbers, which are product of primes. I went there, and so this computer scientist, Umesh Vazirani, explained this algorithm. And in fact, he started with a very funny story. Umesh is a really smart guy, he always has great ideas, all this. And he started this talk by saying, I haven't done anything interesting in the last 2 years, but I've heard about this algorithm, which was going to be called Shor's algorithm. And he says, from this guy called Peter Shor, to factor numbers which are product of prime. And there was a buzz in the conference that this was really important and people were talking about it. At the time, I knew very little about cryptography, so it was very hard for me to really assess everything. But there was really a coherence in that conference. Wow, something's happening here. I came back to the lab and I started to think I was working on something which was called quantum decoherence. And I said, oh, this quantum decoherence is going to be an obstacle to quantum computers. And I started to use little kind of simple models to show that if there would be quantum decoherence, quantum computers would not work. And one day, there is this thing called the archive where we get preprints for everybody around the world. I look at the archive and there's a paper by Bill and Rue on quantum decoherence and quantum computers, giving exactly my message. I said, oh, it's pretty much the idea that I had. So, okay, my last couple of months of work, it kind of goes in the garbage. But then I said, oh, Bill always asked me to argue white when somebody says black and the other way around. So I started to work to demolish his paper. And you never know if these ideas are right or wrong until you go through the whole details of the mathematical models and all of this. So I was poking the other way around to try to kind of demolish his idea. Then I didn't have to say to the other people that I had the same idea. I can say, oh, this guy was wrong. By doing this, I stumbled into quantum error correction, which shows that not all errors will be kind of deadly for quantum computers. There's a family of models of errors that if they happen, there's ways to take care of them. At that time, many physicists thought that this was impossible. And quantum mechanics has this property, it's called unitary. That is, if you make a computation forward, if it is quantum mechanical, it should go backward also. If noise comes in, naively, it seems that you cannot go backward again. So they would say, it's just not going to be possible to do this. The idea at first level seemed to be okay, but if you start to think about it very carefully, it is not really correct. And this is what quantum error correction is really about, is to find a way to be able to go forward and backward in your quantum computation, even if noise comes in. I think I should be a little bit more precise. It didn't show that quantum computation was possible. it shows that noise and quantum decoherence are not a fundamental objection to get quantum computers. So I'll try not to be too technical. The idea is first related to the type of noise that we have. In classical computers, all the information is encoded in bits of information. Bits of information is the smallest unit of information that we have, typically encoded in a system with two levels, and we call them 0 or 1, like something which is either pointing up or pointing down, that little kind of magnetic moment, or a pulse of light which is there or not there, or a switch on or off. So all of the information is encoded in this, and the type of noise that we have is called a bit flip. You have a 1 bit, let's say you want to send it to me. If it is 0, we'd get 0, but suddenly there's noise between you and me, and then it gets flipped to 1 and I get the wrong answer. The idea of classical error correction is not to send your bit one by one, but to encode them so that instead of sending 0 or 1, you'll send me 0, 0, 0 or 1, 1, 1, 3 bit for the 1. And if one of them flips, you can still recover the information just by taking the majority. If there's 2 errors, then it's going to fail, that process. But the process here will take care of the 1-bit error that comes in, which would not have been taken care of if you send it a single bit. So now you try to translate this for quantum computing. There were fundamental objections that this would happen. First, the noise in quantum mechanics is not discrete, like a 0 or 1, but it could look like continuous. The second one is that it seems that when we have taken the bit 0 and encoded it in 0, 0, 0, we've copied it twice. And quantum mechanics tells us that we cannot copy quantum information. And the last thing is that when we try to make this majority voting, then we have to measure the bits. You kill the superposition of zeros and 1. By doing this, then you kill the quantum information. So the question was how to get over this and these 3 objections. And the 3 ways now seems obvious once you know how it works, but it wasn't around the 1990s. And I'm not going to go into all details of how it happens, but maybe I'll mention one thing. So type of noise. It turns out that although the noise can be thought to be continuous, there's a way also of thinking it as being discrete. And the type of quantum noise can be simplified to have either bit flips, the classical noise, or what is called a phase flip. So when we have superposition, there's something called a phase, and this phase gets changed from plus to minus. And the combination of the two makes the type of noise that we have. So the continuous noise that we have can be thought of as a discrete piece, and then we can get over that first objection. There is a theory of quantum error correction, and it turns out that classical error correction is like a subset of quantum error correction. But the advantage is that you can keep these superpositions, and these quantum bits can be in a superposition of being in 0 and 1. There's one way of kind of having a picture of this. You can take the surface of the sphere as the kind of quantum state that one qubit can have. The classical bits are the north and the south pole. We'll call them 0 and 1. But if you are anywhere else on the sphere, then you are in 0 and 1 at the same time. And so these different kind of states allows you to do something different. In fact, the transformation to go from 0 to a superposition of zeros and ones is something that classical computers cannot do. And so by having a quantum computer, suddenly you have different types of transformation you can do with your information. And the hope initially was to find shortcuts, that there would be shortcuts, that if you have different transformation, if you can do some things that your peer cannot do, maybe you can kind of find a shortcut to go somewhere else. And so investigating those right now are all kind of worthwhile endeavor to do. And there's also, I would say, a spin-off of having these different implementation, which relates to not necessarily quantum computing, but to quantum sensors. So quantum sensors are sensors which use, again, rules of quantum mechanics to better sense certain phenomena. They could be better sense the electric field. They could be better to sense the gravitational field. It could be better to field some different properties that we have around. And by studying either atoms or ions or light, then in that case, they can be more appropriate to certain places. If you want to send information which is in an ion trap, quantum information, to your partner who's somewhere else, then you have to use light. And that's pretty hard to transfer the information from one implementation to another one. Suddenly, when transistors were just appearing in labs, totally disconnected, and people didn't think they would be used for computers at the time, appeared, and this changed things completely. Maybe the implementation that we have today of quantum computers are the ENIAC type. Suddenly, we could find some form of artificial particle in material science. Maybe these things, if we can make them in the lab and be able to control them, they would become naturally robust to noise and give us a chance to scale up. This is part of the dream, and we hope that we see these things. In fact, it would be very neat to discover something that kind of suddenly makes it a lot easier, because today, building quantum computers is very hard.